Next week, what's happening next week? Next week, we have a tag team, Vicky and Dave Schreiner, Mr. and Mrs. OpenGL. One of them still working for Silicon Graphics. There is still a conflict. I've heard some horrors, but Sun Microsystems lost 75% of its market value. I imagine Silicon Graphics lost 20% of its market value. Anyway, you can ask those questions next. Next week is OpenGL. Today, however, I just asked Andru how long it's been since he derailed by taking one of my courses, and that was 15 years ago. And today, he's going to tell us how to get lazy.
Good afternoon. Does anyone not have a handout and want one? I tried to give them out as people came in, but then I got distracted. So, with the administrative stuff out of the way, there you go. All right, domain-specific languages. A domain-specific language is a programming language which concentrates more on the problem space, the things, the actions that exist in dealing with the problem than on what you do inside the computer in order to solve your problems. Now, I had an intention of discussing various, I have handouts. If anyone's interested, I'll put them over here. So, I may not run out today. I lost where I was. I was going to explain to you all the great things about them and why you want them, but I had to cut that part for time. So for the rest of this talk, I'm going to assume that you have a desire to implement your own little programming language, and even if you have no idea why. So, skipping ahead, there are basically two broad categories that you can divide DSLs into. There's the external standalone ones. This is basically what we're used to with any other language, but small. These are examples from Unix: some text processing, document preparation, computing, building, creating compilers. There's also embedded, or they're sometimes called internal DSLs. The idea is here you're bumbling along in whatever normal general-purpose programming language you're using, and you get to a place that's particularly suitable for being solved with your DSL, and poof, you start writing in your domain-specific language for a little while, and then you go back. These are a couple of examples from TROF, document preparation in Unix land. For example, EQN, you're going around along, you're writing your paragraph, and then poof, it's time to display a nicely formatted equation. You use a slightly different language for that. Then poof, you're back in where you were. I'm going to discuss a couple of different ways of implementing your own small languages. Some are language specific. Some will work with most any programming language. I'm going to start with the big one, Lisp macros. Basic idea here. Lisp, for any of you who aren't familiar with Lisp, the syntax of Lisp is excruciatingly simple. The idea is you have, I'm oversimplifying a little more even, but the basic idea is you have atoms, symbols, numbers, things like that, or lists, a parentheses, a bunch of other expressions within the closed parentheses. Now what's nice about this is the parser, they call it a reader. The parser is able to parse your program without having any idea what any of the words in it mean. So the Lisp parser has no idea what if means, for example. Now this is convenient because then when you want to go add in your own extensions, the parser doesn't have to have any idea what your extensions mean. So then what happens is you just register with the compiler a macro, it's a little piece of Lisp code that runs at compile time, and you associate it with a name. And then the macro expander runs your code on the tagged code in the input, and you get to do whatever you want with it. You're past the already parsed syntax tree. Right? It's already in a data structure that you can do whatever you want with. You get to spit out Lisp, and then the compiler takes care of the rest. You don't need to modify any other part of the compiler. You don't need to know how it works. This is sort of the gold standard. If you're working in Lisp, you can stop. If you're not, well, stick around. You may also be working in Forth. Now this is sort of a vastly oversimplified version of how a classic Forth interpreter might work. Modern Forth compilers do all sorts of fancy things that aren't like this, but they still kind of look like this to the programmer. So this is a decent mental model. Forth, again, has an excruciatingly simple syntax. It's one word after another. A word in Forth is kind of like a subroutine or a function in other languages. There are some differences, but that'll get you by if you think of it that way. And the basic idea is you've got the one part of the compiler breaks it up into one word at a time, and then you've got the other part. When you're compiling a new word in Forth, the compiler looks up its definition in the data dictionary of all the things that are already defined. Sorry, you're compiling a new word. Words are coming in that are part of its body. The compiler looks one of those up, finds its address, stuffs it into the output, which is threaded code. Threaded code being just the address of a bunch of subroutines to call when it's time to actually run the program. Now, that's what it normally does, right? It looks it up, stuffs the address in the output. However, if the word's tagged as immediate, it runs it right then. This is at compile time. Like with Lisp macros, this is at compile time. You have the full power of the language available to you at compile time, all the standard library, all that fun stuff, data manipulation, everything. You're able to read ahead in the input stream, the characters that are coming in. You're able to generate your own threaded code in the output. You're able to do basically arbitrary extensions. If you want, you could write a C compiler that reads ahead, interprets what's coming next to C, and then does something intelligent with it on the output. People don't generally go that far. But the point is you can extend it in whatever way you like into your problem domain. Some programming languages... C++. C++ templates are typically just used for generic programming. They are actually a Turing-complete programming language that can be used for arbitrary code generation at compile time. Now, it's kind of like programming in raw lambda calculus, so it's a bit awkward. Personally, I've never done it. I would prefer to write a program that generates C++ for me if I were going to go too much farther beyond generics. But if you're interested, there is a book called Generative Programming, which goes into great detail. It explains how to implement loops and conditionals and data structures and all that fun stuff. Some programming languages give you the ability to say, for this little chunk of code, I want you to execute in an extended program, in an extended environment. For example, JavaScript has this with statement. I'm blocking part of the screen here. Let's see if I can move over here a bit so you can all see. JavaScript has this with statement. Now, I forgot to set this up ahead of time. Okay. The basic idea here is the code that executes inside the block is in an environment that's extended by this argument. So what happens is all the code that's executing in here, it's executing in an environment where the members of this object are just there in the environment. So for example, you've got pi here, you've got cosine here, you've got sine here. These are, this is not quite as powerful as the others that I just discussed, because you're still kind of programming in your main language here. But you get some of the benefits. Ruby has this feature where you can take a block of code, you can say, I want you to run this as if it were a member function of that object. Now, if you do this to someone else's objects, you're violating their encapsulation, and that's not a good thing. But if you're doing it with your own objects with code that someone passed you, it gives you the ability to provide a domain-specific language. In fact, if you're very clever, you can even make it look declarative if it isn't. So, for example, this is a piece of TK. TK is a graphical windowing toolkit. This is a piece of TK code in Ruby TK, which just puts up a window that says "Hello World." Now, the stuff between do and end here is a block of code. It executes basically as if it's a member function of the TK label object that was created up here. So now when you say the text is "Hello World," here are the parameters for packing. This looks like you're just passing it some data to use when it's doing its thing. What's really happening is you're passing it a chunk of code. The code gets executed as if it were a member function, and it sets all of these parameters. Right? So for example, pad x, pad y, side, those are all member functions of TK label. But the library author gives us the illusion that we're working in a special purpose language by using this trick with instance eval. Now, these features, this and the width that I mentioned before, frequently come with a warning in your language manual. They say this can lead to very confusing code. Now, I think part of the reason for this warning is because what you're basically doing is, while you're within this block, you're programming in a different language. And if you haven't documented it, if you haven't warned the maintenance programmer who's coming along after you in some way, well, poof, they're in a different programming language and they don't know it, right? There's all these symbols that aren't defined anyplace else that they see. But if you use it correctly, which I don't have time to tell you how, you can make a decent language, that's suitable to your domain, and hopefully reduce complexity. All right, so that's about all I've got on specific examples within languages. There are some techniques that will work on just about any language that you're using. You can create a library. Now, this is more a matter of attitude than technology. It's a design discipline. If you're interested in pursuing, I was going to talk about this for a little while, and I'm cutting this for time, but if you're interested in pursuing this, I highly recommend a book called Structure and Interpretation of Computer Programs. There's a little bit on this subject in the handout. The reference is also in the handout. There's also our old friend, the preprocessor. Now, this is not always the best, but it's very old, very common. A lot of people have had great success with it. All of the little languages I mentioned earlier for drawing pictures and graphs and so forth, and documents in TROP are based on this. Back in the day when Fortran only had one statement after an if, some folks at Bell Labs created a language called RAT4, stood for Rational Fortran. It had multi-line, it had loops and conditionals with multi-line bodies. They implemented it with a preprocessor that basically compiles your extended language into whatever your general purpose language is, and then all of this stuff you just borrow from your environment, right? And this part here is what you add. Now, the big danger with this is confusion, right? The big danger here is if you're not careful, you end up, since you're just working on strings, right? Strings are coming in, strings are going out. It's very easy for a string to end up getting interpreted by the wrong part of the process. If you've done much with the C preprocessor, you're familiar, for example, with precedence problems, if you don't parenthesize all the arguments to macros and things like that. So moving on, the other thing, a very powerful, very general option is build an interpreter, right? Sort of a full-blown interpreter. There are, just like the big boys, only smaller. The basic idea, you've got some form that you represent your program in. Somehow you create it. Somehow you run it. Now, your choice of how you create it is relatively independent of the rest. There are some dependencies, but you get some flexibility there. What you choose for your form does have some impact on what you can do over there. So I'm going to talk about this separate and those two together. On the front end, again, you can do it just like the big boys, only smaller. You can make a full parser. Characters come in, intermediate form goes out, syntax trees or whatever. This is not the easiest thing in the world to do, but there are some things you can do to make your life a whole lot easier. One is use tools. There's a magic phrase you can Google, parser generator. Right? So you put that in quotes, and then you put your name of your programming language next to it, and you'll find tools that will let you specify language. You write out a grammar, in goes the grammar, out pops the parser. And if you're using something popular or old, like Lex and Yak, which are common for C, they've been used by a lot of other people. They've been heavily debugged. This can save you time. The other big thing you can do, if you want to do a full-blown parser for your front end, make your language simple. It doesn't have to look like C. It doesn't have to have 15 levels of operator precedence. Give it a syntax that looks kind of like Lisp. Make everything prefix like Lisp. Make everything postfix like Forth. If you want infix operators, Put them all at the same level. Make them all associate to the left like small talk. Make them all associate to the right like API. I mean, there's a lot of options out there beyond just C and Fortran expressions. You know, if your primary purpose isn't arithmetic, maybe you don't need full expressions, right? So there's ways like this you can take shortcuts to save yourself some work. Sometimes you can use a parser someone else already wrote. For example, if you are programming in Common Lisp or Scheme, if your DSL, if you write your DSL and S expressions, again, just fully parenthesized, stuffed within parentheses, you've already got the Lisp reader. You can use it at runtime. You say, read an expression out of this file, poof, reads it, parses it, done. You've got a parser. There are some other notations that might be useful. There's JSON, JavaScript object notation, that's getting kind of popular these days. There's YAML, it's a markup language type thing that lets you represent data structures. You know, if what you're trying to express is simple enough, it'll fit within one of these, you might be able to just skip writing the parser altogether. It's theoretically possible to do this with XML. But that's a very cruel thing to do to your users. So, you know, please don't make humans write XML. And it's great for data interchange. In some cases, if your programming language has nice enough notation for literals, data structure literals, object literals, and if your DSL is implementing is simple enough, you can sometimes get away with just type the representation of your program directly in as a data structure literal. It's, you know, maybe not necessarily the best practice, but it'll get you up and running sometimes. And finally, my favorite, function calls. What you do, you make one function that creates the doohickey, the node, the expression type for each kind of expression in your language. And then you just call them in order to build up your program. Now, what you get is you get something that looks a lot like Lisp. You know, it's got commas between the arguments, and the parentheses come after the name of the function. But you get something that looks a lot like Lisp. You don't have to write your own parser. You don't have to write your own lexer. You get to piggyback on the language that you're using. Now, in this particular case, I'm being very general, you know, explicitly tagging the variable and the constant. Most of the time, you can get away without that. You can take some shortcuts, but I was trying to show sort of the general case here. Where was I? All right. So that's it for front ends. On the back end, or for representations, one of the oldest, certainly an old representation, very venerable, used by a lot of people with success, syntax trees. What you do, every part of your expression, you have a type, which is a generic expression. It can be one of a bunch of different things. Some of them can have sub-expressions. So here's a structure definition for a syntax tree for a very simple expression language. It's got constant. You can see up on the up here. There's constants, variables, comparisons, and conditionals. Right? And here's the type. Says which one of those is this particular expression. Then depending on what that is. Right? Constants have their own value. Variables have names. Comparisons have 2 sub-expressions. Conditionals have 3 sub-expressions. The condition attests to the true branch and the false branch. And if you're going to interpret these, or you're going to evaluate these, the usual approach, you have a function that takes the expression that's being evaluated and the environment to evaluate it in. That's for looking up the variables that are in there. Then you do a dispatch on what the type is of the expression. Dispatch on type. And I'm going to walk through it for all the cases for this one. I'm going to kind of breeze through it on some of the later ones. But if it's a constant, what you do, you ignore the environment, right? It's always the same value, no matter what the environment is, no matter what values variables have in the environment. It's always the same value. That's why we call it a constant. If it's a variable, we look up the name in the environment. If it's a comparison, this is where things get fun. We do a recursive evaluation of both expressions, and you'll notice the environment gets passed down to the recursive evaluations. And then we compare the two values we got back, right? That's what's going on here. And that's what we finally return. For the conditional, it's the same idea, right? You evaluate the condition recursively. Depending on whether it's true or false, you evaluate either the true branch or the false branch recursively. Now, this is fairly simple. Adding more cases is really just a matter of making it longer. It doesn't make it all that much more complex. This is actually about 45% of the way to an interpreter for reasonable language. You need some more data types, you need loops. Those aren't hard. The big thing that's missing is user-defined procedures. If you're interested in going further down this path, again, I will recommend Structure and Interpretation of Computer Programs. It's in the references. Some of the advantages of using a syntax tree. It's very easy to analyze. Right? If you want to figure things out about your program, you can walk around the tree, figure stuff out. It's very easy to serialize. Again, you can walk the tree, spit out XML for data interchange, shove across a network, whatever. And this is how you evaluate it. All right. Another thing, I'm only going to cover a couple of representations. There are lots. I'm only going to cover a couple that I consider the easiest. Another option is objects. Right? We have the same basic tree structure, but every node in the tree, instead of just being a structure, it's an object. It knows how to evaluate itself when it's given an expression. So it's got we've got a virtual function that's evaluated. It takes an environment. It returns an integer in this case. Right? So my programs take an environment, they return an integer. That's what a program is in this little world. Constant, this should be looking familiar, right? We have a value, and then when we try to evaluate the constant, we ignore the environment, we return the value. And I'm going to skip down to the quality test. Right? We've got the two sub-expressions. We're going to compare for equality. At runtime, when we try to evaluate this expression, we have to evaluate both of the sub-expressions, and then we return that value. Now, this is harder to serialize. Some languages will let you serialize objects. In many, it's not that easy. You can still walk the tree, for optimization or analysis or whatever if you want to. And this is how you evaluate it. All right. So moving on to closures. This is the third and final representation I'm going to discuss. Closures are a package that contains some code to execute and an environment to execute it in. C and C++ do not have this feature. My examples here are going to be in Perl, but a lot of recent languages have them. Common Lisp, Scheme, Perl, Python, Ruby, JavaScript, they're around. The basic idea here, and this little bit here, I'm not going to try and teach Perl today, but the basic idea, this little bit here is saying augend, this is a function of one argument, and augend is the name of that argument. And what this does, makeAddr takes one argument named augend, and then it returns a closure. Now the closure has this code, the code after the sub. And you can't see it. There's no real way for me to illustrate this. I mean, I could draw pictures on the whiteboard, but there's no way to show it in the program text. But it's in whatever the environment was when that return statement was executed, or when that sub-expression was evaluated. So the example down here, I'm making two of these, right? Add 2 equals makeAddr of 2. Now, add 2 is a procedure, it's a function, closure. Add 2 is a closure. It is a closure that will execute this code. It has this code from this subroutine. Clean that up. It has that code from that subroutine. And it's got an environment where augend is 2. makeAddr 5 down here creates a closure. It's got that very same code as the stuff that as add 2, but it's got a different environment. It's got an environment where augend is 5. And down here are the examples. I don't know if everyone can see all the way to the bottom of the screen. It's in the handout too. When we call add 2 with 10, we get 12. When we call add 5 with 10, we get 15. The point is these are different closures. They use the same code, but they have different environments. It's also possible to put little procedures together to make big procedures. This is the compose function that we're all familiar with from algebra, right? I'm sure you remember F and the little round circle and the G. And that's, when that's applied to something, it's G of that and then F of whatever G returns. Well, this is the same idea. Right? compose gets called, gets given two procedures, and then it creates a new procedure, or closure, in this case add 7. Right, so I call it with add 2 and add 5, so that's procedure 1 and procedure 2. Then at runtime, so when I call add 7 here with 10, what's actually going to happen, it's this code, it's run in an environment where procedure 1 is add 2 and procedure 2 is add 5. Procedure 2 gets called on the argument, so 5 gets added to 10, returning 15. The result of that 15 is passed as an argument to procedure 1. Procedure 1 is add 2, 15 plus 2 is 17, out pops 17. So there's sort of the 2-slide crash course introduction to closures. All right, so how does this apply to representing programs? Well, if you don't need to serialize a program, if you don't need to analyze it, one trick you can do, you can build up a program which does what you want to do. You can create a procedure which does what your little special purpose program is going to do. And you start by defining your interface. You go, okay, a program in my little DSL is a procedure that takes an environment as an argument, and in this case returns an integer. Okay. And then you have these other functions that are going to create programs. So for example, constant. Right? It's passed a value as an argument. It creates a program which takes an environment as an argument and always returns the same value. Variable takes a name, creates a program that takes an environment, looks that name up in the environment. Equal, same thing. Takes the two arguments, the two sub-programs, right? Expression 1 and expression 2 are the same type. They take an environment as an argument, they return an integer. It returns a new program of the same type, takes an environment as an argument, returns an integer. It works by running the two subprograms, right? It runs expression 1 on whatever its environment is at runtime, runs expression 2, compares the values. And I'm going to skip that for time. Okay, here's a little example. This is the same example you saw before. And I've got an environment up there. X is 10, Y is 20. If X equals 100, we return 1. Otherwise, if Y equals 20, return 2. Otherwise, return 3. Well, X doesn't equal 100. Y does equal 20, so it ends up returning 2. All right. Now, any of these approaches will also work if you want to create code. Right? Instead of running your little program, if you want to create code to run later, what you do, instead of doing something, you spit out the code to do that something. This is sort of a general way any interpreter can be turned into a compiler. The big thing that will save you effort here is you don't have to generate assembly code. You can generate anything you want. You can generate C. You can climb up the stack higher. You can generate Perl, Python, Ruby. You can even generate shell scripts. You can generate the same language that you're using for the rest of your project. Well, then the things that you create using your DSL and stuff you create manually, they can call each other. They can share data structures if you want to do that. You can use templates for the code that's generated. That's nice. That separates the logic in the generated code from the logic that creates the code. So then, especially if they're the same language, that can save you from some confusion. Some languages have an eval feature. Again, Perl, Python, Ruby, a lot of basics, common Lisp, scheme. The idea is you have some data structure, usually a string, which represents a program in the current language. You call eval on it, it runs it. Well, one option, you can generate a string that is your program and then run it. You have to be careful about injection attacks and security things if you're, taking data from people you don't trust. But in the general case, that's another thing that can give you some shortcuts. Never edit code that was generated automatically. Pretend it's binary, pretend it's object code. The real source code is the code in your DSL, right? If you're doing code generation, the code that's generated automatically, you can play with it for debugging, maybe. Don't ever let code you edited by hand into production, right? You change your code generator, you change your original program in your DSL. That's the actual source code. That's what you maintain if you go this route. And that's it for my sort of whirlwind survey of techniques. I've got a few examples here. And I'm looking around the room, I'm wondering, is there anyone who finds this screen familiar? Am I?
A little bit.
Okay. A long time ago, back before web browsers were popular, being on the internet was usually accessed in text using a terminal. And our library, which was in this very building, it was called the Ruben Salazar Library at Sonoma State University. Now it's the SSU Library, much shorter name, easier to say. But we had a bunch of these VT320s. They were these terminals. They just showed you a screen full of text, 80 by 24, and they had a keyboard. And there's this program, it was called Libs. It was written by Mark Resmer, former director of IT. Back then it was known as CMTS. And what it did was it gave you this little menu interface that let you browse a list of all of the libraries that had catalogs on the internet. And then you could connect and search them. The internet was a lot smaller back then. And this would, well, okay, here's a sample screen. This is the screen of California libraries, obviously. You can see at the top. And one fun one right here is us. Here's what happens when you pick SSU. You get a little prompt, you get some instructions for what to do when you're connected. These instructions don't work anymore. The computer that this is for doesn't exist anymore, at least not on this campus. It asks you if you want to connect. If you say yes, it'll connect you. Now this whole sort of menu-driven program thing was controlled by, there's this mile-long program written in something called ISL, Internet Services Language. And it had entries for each menu, and it had entries for each thing you can connect to. And I got to maintain this for a few years in the early 90s, after Mark Resmer stopped. And here, for example, is the entry for that California menu. All right, what it says is, put a label into ElMenu, which is the identifier for US libraries. I have no idea why. Call it California, right? So when you're looking at US libraries, there's going to be a label in there called California. When the user selects that entry, show them a menu with 34 options. It's going to be called libca for any future things that go in it. And the heading that goes at the top of the screen is California libraries. Here's the entry for Sonoma State University. Right, there's the S label again, right, saying put an entry into libca, give it this name in the menu. Now here's an interesting thing. This was very new to me when I first saw this. Anything that doesn't start with a dot turns into a print statement. This is an example of optimizing for the common case. Most of the time, what you want to do in this thing is show things to the user. So make it as little effort as possible, in this case, none. Instruct as a macro prints out, pay attention to the following. Then this gets displayed. This tells you how to quit, which changes depending on what system you're on. And then the telnet back Sonoma Edu says, ask the user whether they want to connect. If they say yes, then run a telnet session to this host, which doesn't exist anymore either. If you try to connect, you're not going to find it. So there's this mile-long file that's got these definitions for all of these libraries that some poor student assistant, me, got to go through and test all of them. And then this gets chewed up through two Pascal programs. One spits out a mile-long .com file for VMS. It was a batch scripting language, DCL, digital command language. The other one spits out about 500 shell scripts for Unix. And then this is what gets distributed on the website, or actually it was an FTP site back then, to all the users who want it. By the way, both of those Pascal programs used GoTo. All right. So moving a little forward in time to the present, in IT we have in computer operations in IT, we are the server group. I work with the sysadmins. We have an inventory database for keeping track of all of our computers and other sundry things. Now, we tried to find other software that would do what we needed. But one of the problems that we discovered was our main problem that needed solving, nothing out there really addressed. And our big problem was the fact that we're never absolutely certain what we want. There's always something else that comes along that we want to track about things. And so we really wanted the ability for the sysadmins to go in and say, okay, from now on, for a server, we also want to track the hardware manufacturer. We also want to track, we needed this ability to make some of these changes on the fly without having to put in a change request, have the programmer spend a bunch of time modifying the actual program. Well, long story short, the database schema isn't all that easy to access directly. You really want to access it through a library. And this library has a bunch of features, adding, removing, so forth, but the one that's of most interest today is query. Right? In order to do a search, we've got a little query language. And this query language lets you specify things about the object you're searching for in our inventory database. So this query here is active. Now how you actually use, this is creating a query. Okay, now these function calls don't actually run anything. They just create the query. I'm not going to talk about how it gets run. But this is creating a query called isActive. We say a server's active if, let's see, if its status is null and its system lifecycle stages either has OS or in use, or if its status is surveyed, if its status is storage, is equal to storage, or if its status is like surveyed. There's a little wildcarding there that will look familiar to those who use SQL. Is server, is the name of the type of this object server. Now, one of the great joys in life is when you create a tool and one of your users uses it in a way that you didn't expect. Right? Because what that means is you manage to create a tool that's good enough and flexible enough that it was useful beyond its sort of original design. Well, one of the things that one of my colleagues realized was, well, storing it in a variable or using it as an argument to another function is basically the same thing. Hi, Eric. So the idea here is, okay, so we've got this isActive query, but we can use it in building up other queries, right? So we can say, okay, my Solaris boxes are the ones that our servers are active and have an OS version that looks like Solaris space and anything. Similarly, we can say, well, my Dell boxes are servers that are active and have a make that starts with Dell. All right, remaining in the present. I lost track of our other. Okay, remaining in the present. We have an identity management system which keeps track of you, what courses you're in, what services you have, and whether you've got an email account or not, and things like that. When you last changed your password, all this fun stuff. We also have people in IT who need to access this, right? You walk into our help desk, you say, I forgot my password, you show them your ID, they have to do something. So we have this IT services manager that's used for interacting with this data. Not everyone who uses it has the same kinds of access. Not everyone who's in it can be accessed the same way by everyone. And not all the information we have about you is made accessible in the same way to the same people all the time. So when a person using this application looks someone up and goes around, maybe wants to edit something or wants to look at something, a decision has to be made. What level of access does this person have to this attribute on that person? How do we answer these questions? With a domain-specific language. It's rule-based, it's first match. The basic idea, we've got this big long list of rules. A rule consists of a condition. So for example, here's one rule right here. Okay? So the rule consists of a condition and a result, right? So here's a condition, and here's a result. Both is read and write. Okay, so there's many different kinds, but there's two popular sources for how people get into our identity management system. There are folks who come from PeopleSoft, That's students, employees, most everyone in this room, I believe. Then there's folks who we don't track in PeopleSoft, but we still have to provide services to. So this is consultants. Hi, Susan. She's not a consultant, but she's also one of those people for the moment. The Center for Distributed Learning actually is part of the Chancellor's office. They're not in PeopleSoft, or in SSU's PeopleSoft right now, so we have to track them separately. So we have this idea of a source, where you came from, right? If you come from, where did our information about you come from? I mean, where you came from is kind of a philosophical question. But like, did our information about you come from PeopleSoft, or was it entered by someone in IT? So our rules here, these are just sort of 4 example rules that kind of implement 2 ideas. If you came from PeopleSoft, folks in IT really shouldn't be editing most of your information. Most information that came from PeopleSoft should only change if it changes in PeopleSoft, right? Your name, for example. However, there are some things that they should be able to edit. And so what we have here is we say, okay, if the person being accessed is from PeopleSoft, if the person doing the accessing is in the IT group, and if the attribute that they're accessing is one of those, we'll give them read-write access. Otherwise, remember, it's first match. Otherwise, if the person being accessed is from PeopleSoft, the person doing the accessing is in IT, it's read-only. Down here we have kind of the opposite case. This is for someone that we put in, right? Because almost all that information is going to be from us. Only certain sort of security-sensitive things will we not want someone to read or write. All the normal stuff, again, your name, we have to put in, right? Because we're creating the record. So if the person being accessed was entered by IT, the person doing the accessing is in IT, and it's one of these sort of sensitive attributes for some reason, then you only get read access. Otherwise, again, same basic rule, right? If we entered you and it's one of us accessing you, then we get read-write access. I'm trying desperately to finish with a few moments for questions. You know what? I've got one more example. Do you want to hear the last example? This is future. This is something that hasn't been implemented. Do you want to hear the last example, or do you want to ask some questions? Okay. One of the sort of on the horizon things that we've got going in the CSU is a technology called Shibble, which is very, very cool. It only works for web apps, but within that domain, it's very nice. What it does is it solves the basic problem that the server that knows who you are, that knows how to authenticate you, that knows what level of access, that knows how to authenticate you, that knows what kind of person you are, whether you're a student or an employee or whatnot, it's frequently not the same server that wants to provide you a service. Especially when you start crossing institution boundaries. Right? Wouldn't it be cool if we could go to San Francisco State, or one of their students could come up here and log into our wireless network, for example, using their credentials from back home? Well, that might be possible within a year or two. So this is a sample from a prototype, proof of concept that we implemented. This isn't actually happening yet, but there's plans at a system-wide level to make this happen. And it's, anyways. So when we log you in, we need to decide what level of access to give you to the network. For example, we might give employees a greater amount of access than we give students. We might give local people more access than we give someone from San Francisco State. So we have this concept of roles within the wireless access point. Well, somehow we have to decide what role to grant. Well, here's where the DSL came in. And there's 3 examples here. If the issuer is where we got the information from you. Right? So if the issuer is paddle.sonoma.edu, we got the information from here. Right? So you're an SSU person. If your edu-person affiliation is employee, that means you're an employee here. So, and again, remember, first match. So if those 2 match, we give you the employee role. If they don't, we check to see if you're a student. If they match, you get the student role. Now, this order is very important because a lot of people are both. There's a lot of overlap. And so that's actually one of the great challenges of identity management, is there isn't really a good concept of, there isn't really a good answer to the question, what kind of person are you? Which is something a lot of people always want to ask. Right? What's better is if you can design a system so it always asks, are you a student? Are you an employee? Yes or no? Are you a consultant? Yes or no? If you can keep those as separate questions, things get easier. but you can't always, and this is one of them, right? You only get one kind of access to the network in the login. Let's see. So well, if you're not one of us, if you're an employee from some other campus, we'll give you the external role, and everyone else gets an error message, right? This is a rule that just always returns true. And that is all I have, and are there any questions? Do I have any?